We present range-conditioned dilated convolutions for 3D object detection. The basis for many 3D object detection techniques is this of voxelization. This is where points are discretized into a regular grid and locally aggregated to form voxel features. Using a 3D convolution in a sliding window fashion. Another common approach used in a similar fashion is to project the points into the bird's eye view, where 2D convolutions can be applied. While these techniques benefit from a consistent scale, they're also limited where, as objects further away from the sensor have fewer points, this sparsity, along with the loss of information in aggregation, makes it very difficult for these techniques to detect objects at long range. In this work, we make use of the native range image representation, where the range and echo properties of each point is encoded into the pixel values. This compact representation allows us to make use of efficient 2D convolutional-based detectors for this 3D detection problem. However, in this view, objects at different ranges appear as different scales in the range image. The key contribution of this work is to address this problem by creating an adaptive, dynamic, and continuous dilation operation where the kernel of a convolutional filter can be adjusted based on the range to the object. By directly using the measured range, we can adjust the dilation to account for the different scale of the object. This maintains a consistent sampling relative to the object's size at any distance. For a nominal width of a given object, represented as lambda, we can estimate the amount of dilation required using the range within a trigonometric function. The overall pipeline of detection looks as follows. The input representation is fed into a 2D convolutional architecture where we process this input at different scales. The output of this is proposals, which are then fed into the final RCNN framework, where 3D convolutions are applied locally to refine the proposed boxes. The core novelty is in this central region proposal region because we apply 2D dilated convolutions, which can be inserted at different layers in this backbone network. The actual module for adjusting dilation is composed of this spatial transformer where the input pattern of the local points are then transformed and scaled based on the location of the pixel and the input range at that pixel location. The features from pointwise convolutions are then remapped according to this spatial sampling, where the final pointwise convolution is where the weights are applied to these different spatial locations. In an ablation study, we compare our method to a standard convolution, dilated convolution, and the ASPP module with multiple convolutions. We find our method to be the best performing even with a single RCD layer at the start of the network. With the addition of multiple RCD modules throughout the network, we see further gains in this region proposal stage. Finally, including the 3D RCNN module, we overcome issues around occlusion, where the 3D average precision is the best performing based on our backbone. Our approach shows significant benefits over LaserNet, which is a similar range image-based detector and is competitive against state-of-the-art voxel-based methods, especially at long range where we are outperforming by a significant margin. In this scene, we make a qualitative assessment of the quality of the detections. We can see that the predicted boxes in red overlap quite well with the ground truth in yellow, not just in the bird's eye view, but also in 3D where the height is well aligned. Even for this difficult scenario, where even for a human, it is hard to tell whether this is a false positive or just a missing annotation, we're able to detect objects quite reliably up to the extremity of the laser range. Thank you for watching.